Hi everybody, welcome back. I would be totally remiss if I didn't take a couple seconds here at the beginning of this video to thank all of you who commented on the last video. They were very helpful comments, and if you guys get a chance, go back through and read some of the comments section. There's so many good things in there that people offered about how this thing works. One of the things I need to kind of share with you is that even though a lot of you did share with me links or actual files of schematics for this particular receiver, but believe it or not, none of them, not one, is a perfect match for what we have here. And we'll get more into the differences. This is a different board even than the schematic that I have that shows the vacuum tube front end. So it's been a little bit of a challenge figuring this out. But the first thing I want to do is I want to go through some of the things that some of you commented on and how helpful it was. First of all, I had several of you say that the right here, which we're looking at the 38 kilohertz, and we talked about that earlier, how the 19 kilohertz is doubled out of this one transformer and goes into those two diodes that give you a 38. It's basically a frequency doubler circuit. And several of you said, I don't really like the shape of that waveform. And I made a comment. I said, it doesn't look very good, but as long as it's 38 kilohertz, we did the math, it should be good because the timing is what's important. Well, what I found out is this coil down here, this little transformer, had a double peak in it. And one of you had mentioned that, possibly this thing's just been so power tweaked over the years that something's way out of whack. Well, that turned out to be the case. This had a double peak on it, and when I ran the slug way, way, way in, it went dramatically out of adjustment. Then all of a sudden, that frequency started coming back up again, and we were getting our 38 kilohertz. And when I was done, take a look at the result. Much better than it did in the last video, isn't it? Take a look at that. So we now have a pretty nice looking 38 kilohertz signal. Now, it's not a perfect sine wave, and I think there's several reasons for that. First of all was, when you connect test equipment to something that's a very low signal, I'm at 50 millivolts per division. Anything like that could affect the shape of the waveform a little bit. So again, this is really good, and I think this is going to be just fine. Now, overwhelmingly, some of the most comments that I got was dealing with the diodes, the detector diodes, which are germanium diodes. And everybody made the suggestion I should just pretty much wholesale replace all of them because they have known issues. Well, I agree with that because, again, the ones that I replaced made a big difference up here. So I did replace the detector diodes here at the bottom, at the output of the, that detects the left and right. And these are just before the de-emphasis modules, and we'll get into all that later. The other thing I found was, if you notice from the last video, there have been a large number of resistors replaced in here. Now, I'll start out by saying not all of them were bad, but I will say a very large percentage of them were very, very out of tolerance, including on a schematic, right here, this 5-point K was very high. It was bad. Some of these 33Ks, all of the 10Ks, I don't know what it is about them. They look like the same manufacturer of resistors. They're all carbon comp. But it seems like every resistor that was a 10K, when I took them out and tested them, they were all reading really high. That's kind of strange. The 1K resistors all held their values. They were all still reading very close to 1K, well within their tolerance band. But the 10Ks were all bad. So I ended up replacing quite a few of those. The little capacitors weren't very bad. I didn't see any problems with them. This 0.01 was a little bit flaky, so I just went ahead and replaced it. That's this little white film capacitor right here. And it was a film capacitor before, so no, we didn't mess with that. Now, I know I'm getting a little long-winded here, but a lot of you are interested in this stuff, so I'm going to put it out there. When you replace these resistors, everything on this module is audio frequency level. In other words, it's, 38 kilohertz is the highest frequency this board sees for the most part. So it's really not a problem on these when you replace the resistors. But just keep in mind, anytime you're working on a tuner, especially when you're in the front end up here, the RF or this IF section here, you have to be careful with what type of resistors you use. Some of these carbon film and metal oxide resistors have a kind of a spiral cut resistive material, and that spiral cut resistive material actually has an inductive component to it. Now, everything that's a conductor can be an inductor. In other words, even at high enough frequencies, even the leads on a component can have some sort of inductive component to it, but usually it's so small that it doesn't affect the circuit. But these resistors at VHF and UHF frequencies can affect the circuit. Carbon comp resistors do not have that problem. So it's something you have to keep in mind. There are metal film and carbon film resistors that are considered non-inductive. In other words, they have very, very low inductance to them. When you purchase them, you want to make sure that you be aware of that anytime you're working in the high frequency section of a tuner. Again, not a problem here because everything in here is audio frequency. So we're not worried about it. So now let's look at a few more signals in here. After getting this thing adjusted properly, after replacing those diodes there and these diodes here, I also found that these two potentiometers, and again, those are at the output of the multiplex detector circuit. See right here? So this is where you're actually demodulating the left and right from the composite signal here. You see these little balancing potentiometers. Well, they were supposed to be 50K. Supposed to being the key word here. Let's take a look at what they were. So here's resistor number 1, or potentiometer number 1, I should say. Yeah, you're reading it right. That's supposed to be 50K, and it's 79K. And this other one, $97K, so it's double what it should be. These pots are a mess. I've had to end up replacing almost every single one in this receiver. And the reason being is when you look at these old Bakelite potentiometers, anytime you see these in really old audio gear, you want to really scrutinize them. The carbon material, you can see it, is just a track that goes around here like this. And it's held on by a rivet. Do you see that rivet going through there? So here's the terminal, there's the rivet, and the rivet makes contact between the carbon track and the contact. And if those loosen up, there's not much you can do. And if you try to kind of tap on it or, crush it down, it ends up cracking that carbon and it doesn't make good contact anymore. And you get problems like what you see. So those should be replaced. And once I replaced those, that made the greatest difference. Now let's kind of step through now. We're going to put a 400 hertz audio tone now on our carrier. And we're going to move over here, and we're going to look, get on a schematic here. We're going to look right here at this output, right here on pin 1 and pin 1 here. So these are your FM de-emphasis modules. So these are what put that de-emphasis on there. Every receiver has pre-emphasis, you know, every radio station, depending on what country you live in. There's two different, go into my, I did the video on multiplex and FM and so forth. I talk about that. But that's what this does. This is what adds the de-emphasis to it and supposedly smooths out the audio. So we're going to look right here, and what we should see is just a nice 400 hertz tone, which is the audio that I'm putting in for my signal generator. So we're going to go over here. I'm going to pop the end, the witch's hat off of the probe, and I'm just going to probe right here at the output of each one of these. So I'm going to go here, and I'm going to go over here. So this pin 1, and we're just going to look at it on the scope. So let me get you up on the scope, and you'll see what we're going to look at. Okay, we're up. Our camera's on. So here's channel 1. Isn't that a pretty looking sine wave? There's channel 1, and there's channel 2. And they're very similar. Channel 1's a little bit cleaner. Channel 2. So they're not perfectly matched, but they're very close. And we do have stereo right now, so we'll get more into that later. Now, let's look at the output of those modules, which is going to be, sorry, hope it'll focus, pin 3, which is here and here. All right, so let's take a look at that now. Let's see if I can get on there. And it's not too bad either, but take a look. The one channel is starting to get kind of distorted looking. So what that tells me is that these de-emphasis modules are probably bad, at least one of them. And if you look inside there, excuse my reach here for a minute. If you look inside there again, you can see there's 3 capacitors and 3 resistors in each module. And you see how precision those are, 510 picofarads, 430 picofarads, and 82 picofarads. They're very specific values, and if those values drift, what's going to happen is it's not going to de-emphasize the signal properly. So let's take a look once again at that one with the funny looking signal. That's 400 hertz. There's 1 kilohertz. Looks about the same. 5 kilohertz, look what happens. Did you see how much the amplitude went down from 1 kilohertz to 5 kilohertz? So there's 1 kilohertz and there's 400 hertz again. So no doubt those will probably need to be replaced. If you wanted this thing to work perfectly, that's what's going to happen. Now, if we go to the other channel, I probably should do the same test for you, so you could see it as well. So here's the other channel that looks a lot better. See that? And if I go 1 kilohertz, 5 kilohertz. Now, here's where things get interesting. This is the output at the record jacks of the receiver. So what you're looking at now is the very end of the circuit, which is all the way the output of this little amplifier. So this is just a little amplifier. It just amplifies the output of the audio, and you're looking at these two outputs. They go out to the switching and everything and goes to the record jacks. Yeah, that is really, really bad. Nothing looks right from there. If I go to right channel, you can see now it suppresses the channel. And if I go to left channel, it suppresses the other channel. But you notice left channel, it suppresses the right channel very well. Do you see that? But when I go to right channel, the left channel is not being suppressed very well at all. And you can also see there is some horrible distortion. If I go back to straight stereo. So I have stereo now. It works. I do have channel separation right and left, but look at how distorted those are. That is being done by that little amplifier circuit. So let's look at the schematic. Okay, and you're going to see a shaky camera throughout parts of this video because I kind of have everything positioned close to one another and the camera is kind of in the middle of all the action, so I can move back and forth. So I will bump the camera from time to time. You're just going to have to live with it. So the first thing I'm going to show you is they're showing in this section that Q4 and Q5 are two SC401s. And those are actually very old NPN silicon transistors. And they look like this. So they look like the old germanium ones, but these are actually silicon transistors. But when I pulled these out, lo and behold, if you look, they are 2SC281. You see that? I don't know if you can see that in the camera, but they're a 2SC281. They're not the transistor that's in this schematic. But what gets even more interesting is when we get to this section here, and these components, some of them are different. They're not the same values, and they're not even configured the same way on my board. If you get to this one, you can see very clearly these are NP or PNP transistors, and they're 2SB439s. Guess what? When I pulled them out, they're not PNP, they're NPN, and these were germanium. They're not. It was another pair of 2SC281s. So there's 4 of these NPN silicon transistors, and by the way, they cross over very well to just a standard BC547 transistor, all 4 of them. So the biasing is different in this circuit, the polarity is different in this circuit, the values of these components are different in this circuit. This whole thing is different. And throughout this whole board, there's little subtle changes that have been made, and they do not match this schematic. So that's, interesting. And none of the schematics I have those changes in them. So this must be either a late change that was done, and I think it was a late change because the new board in the new output, let me see if I can find it, they completely changed it and comes out of here and it just uses the input from the tone control section. It doesn't even have that buffer amplifier anymore. And the de-emphasis is done by discrete components. There are no more little PC board thingies with, couplet modules. Much more streamlined, much simpler circuit, you notice? So much improved. I think this was the in-between circuit. And when we move over to here and we look down, this is that section. You can see where they've removed components. You can see where there would have been a drill hole right here, but you can see they moved it over and they didn't even mark it. They just drilled it and put it in there. This is factory. This is not something somebody did. Throughout this entire circuit, you can see where this has been changed. Okay, you'll have to excuse the convoluted nature in which this video contains right now, because I've had so many comments from so many of you that I'm just trying to cover that as well as troubleshoot this. So if you notice, there's this yellow and orange line on here. Those are the only two connections to the outside world that this pilot detect board has. I'm going to call this the pilot detect board, because all this board has one job and one job only, and that is to recognize when there's a 19 kilohertz pilot tone in the multiplex signal, and then do two things. Number one, turn on the light. Okay, so it'll turn off the mono, turn on the stereo light, and then you can see there's a connection here, and there's a pull-up voltage. There's about 6.7 volts here in this little voltage divider. Maybe I can zoom you in a little more so you can see better. And if you notice, it goes up into the center tap of this transformer. It has a little capacitor on it. And actually that 6.7 volts is only present when it's a mono signal. So this is an active low signal. In other words, when you have a 19 kilohertz tone, this will actually go low. It'll go close to 0 volts. It'll go to a voltage drop. You know, you'll get 0.6 or 0.7 volts. So it takes that voltage out of the equation and allows this thing to do its job, to oscillate. This center tap then just becomes, you can see there's a capacitor here and then two resistors going to ground, and that's it. But when this thing goes up to 6.7 volts, it kind of squelches out this circuit over here, and the only thing you get is the audio coming into this center tap on the other side, the secondary of this little transformer. So that's how that works. But the main shift between stereo and mono is this going low, and then these two coils recognizing that there's 19 kilohertz there. So they're tuned to 19 kilohertz. If there's no 19 kilohertz, this collector, the signal on the collector of these two transistors is very, very low. There's almost nothing. So you have very, very little of the audio getting through this and getting into this transistor. And what little bit does get to here gets drowned out by this 6.7 or 6.8 volt level right here. So those two conditions have to be met. And as soon as you hit 19 kilohertz here, it kind of floats this up. This acts like a frequency controlled switch when you think about it. When there's 19 kilohertz, that 19 kilohertz will light this up here, I'm using my own terminology, and it'll carry with it the 400 hertz and so forth, but or whatever your audio is, but it doesn't matter, because all it cares about is we want 19 kilohertz and we want it to be a strong signal, and then we're going to go through these two diodes, and that's going to double the frequency. We talked about this in the last video, and you'll have your 38 kilohertz here. And that 38 kilohertz will go through here, and it'll resonate in this tuned coil here if you tune it properly. And this voltage goes away, so this no longer has an influence on squelching the circuit out. And that 38 kilohertz once again mixes with your multiplex signal, your composite signal that's here, and then it gets detected here and here and becomes your left and right. And then it goes through your de-emphasis, and then it gets amplified and buffered and goes out to your stereo, to your amplifier. So just wanted to review that. Now, what we were looking at was everything looked pretty good here and here. So your left and right are looking like left and right signals when they're here. But as soon as we get through this de-emphasis signal, we already start to see some distortion, don't we? And as we get through here, you're going to see it's going to get way, way worse. So here's our plan. I have removed this capacitor and this capacitor. So we are essentially separating this side of the circuit from this side of the circuit. And the first thing we want to do is let's take our scope and let's just look at these outputs right here and here. I just want to see what they look like with the proper, without the influence of any of this being connected to it. We just want to see what we have. So that's what we're going to do. And if I move you over here real quickly, I will show you that we have removed, there's right there and right there, you can see the empty holes. So those 1 microfarad capacitors are now out of the circuit. And we're going to go up here to our scope. And we're just going to look at what we have. Okay, so the output of our multiplex board, or our multiplex circuit, and this is coming out of the de-emphasis. There's one channel, there's the other channel. And again, I think those de-emphasis modules are not in the greatest of shape, but there's what we have right now. So I would at least say that they're equal and that they have a relatively good amplitude, because I'm at 200 millivolts per division. We have a good signal coming out of there. So now what we want to do is we want to inject our own signal into it. And here's the signal I'm going to inject. I have just a 400 hertz audio signal. And if you look, let me change the scale. It is 200 millivolts peak to peak. So you can see it's going positive 100 millivolts, negative 100. Very nice, clean 400 hertz sine wave. So that's what we're going to inject into this amplifier, and or into this little amplifier section, right where that capacitor would be. So we are going to actually inject it right here and here. And what we're going to use to do so is something you can make yourself. It's a really simple little device. We're going to use this. And you've seen me use this on tuners before. All this is a 1 microfarad non-polarized capacitor. You could use a film cap or whatever you want. And if it'll focus, there it is, see? 1 microfarad. And I just have it connected to a simple little BNC jack. So the output of the jack, and then I just have one of these little aglets, little terminal aglets. I just soldered it onto the end of the terminal, and it just makes a little mini isolation probe. And what that's going to do is that's going to block any DC from getting back into my signal generator. That's all. I use ones of smaller value for RF, injecting RF into different parts of a receiver. But this is for audio because it's a little higher. You can see it's 1 microfarad. Anyway, let's get focused on the output here, and I'll show you what happens when we connect this signal, just a pure 200 millivolts peak to peak sine wave, into that circuit. And we'll do channel 1 and channel 2. So here we go. Here's channel 1. And you can see we're getting a 400 hertz signal, but it's very, very noisy. But more importantly, look at the crosstalk on the other channel. It's pretty bad. And then if I go to the other channel, it's lower amplitude. First of all, you notice. I'm sorry I keep moving around here. It's hard to hold the probe on. And really bad crosstalk on the other channel. So there's one channel, other channel. And notice one channel has a lot higher amplification than the other. And look at the noise. The noise is on all the way around on that side. The noise is only on the bottom on the other side. So something is not right in there. Something is not right. So let's take a look at what it possibly could be. So some of you may have already noticed that I highlighted this little loop here in pink. And yeah, eat your heart out, Big Clive. We used fetching pink. So anyway, you can see we have this 100 microfarad capacitor. It passes through this potentiometer and 0.005 microfarad capacitor. And then it goes around into the emitter of this side, so it ties them together at the emitters. The first thing I want to see is if something in here is causing our problem. So I'm going to remove this 100 microfarad capacitor, and we're going to try our same test that we just did and see if, number one, if the crosstalk goes away, and number two, if the noise goes away. Okay, we've now removed this 100 microfarad capacitor. So now we have this removed, and this removed, which essentially this takes this whole little circuit out of the picture. And these two, once again, take everything before this out of the picture. And we're now going to put our signal generator here and here. So this is Q4 and Q5. Then we're going to put it on Q6 and Q7's base. We're just going to go right to the input here and here. So we're going to check and see what it looks like here, and then what it looks like when we inject the signal here. And remember, this is just a 400 Hertz audio signal. So let's move up to the scope. And again, we're still looking at the record output jacks of the receiver. Okay, so first things first, let's look at the base. We're going to inject the signal in the base of Q4 and Q5. So here's Q4, terrible, and Q5, even more terrible. Now let's go to Q6 and Q7. Look at that. Q6, really nice. Q7, really nice. And the only thing I can tell is, you see that one right there? You can see how the sine wave is not quite, the amplitude is not quite 3 divisions. And if we go to the other channel, it's right on 3 divisions, and it is scrolling because I have the triggering for the scope set on channel 1. So since there's nothing there, it's not triggering. But you get the point. We have a nice pure sine wave on both channels. They are a little bit different amplitude, so I still think we have a bad resistor somewhere again. But we're passing a good signal on Q6 and 7, but for some reason that the front end of that amplifier, Q4 and Q5, definitely has something wrong. We don't know what it is yet, but something is not right with that. Now again, the schematic that we have down here does not match the schematic, or what's actually on this board. So looking at all of this, some of it is similar. For instance, we have the 100 microfarad cap. We have the 5K potentiometer. We have the 5.005 microfarad disc capacitor. That's all there. These are here, the 1 microfarads. The coupling capacitors here, the 10 microfarads, are here. And so that part's right. But when we get into this section right here, it's different. Because number one, the emitters and the collectors obviously have to be swapped around because, or I'm sorry, over on this side it's different because this is showing a PNP configuration, and these actually have NPNs in there. These are NPNs, so it should be similar, but for instance, this resistor here, this 560K, on the one we have in front of us, it's not a 560K, it's actually like a 260K. It's a different value. And like I said, the 680 ohm resistors are not there, I believe. if I recall correctly. So a lot of these are different. The 8.2K resistors are not there. They're different. So all of this is different. So what I need to do is sit down and figure out what it is. And the thing that we don't know is we're not 100% sure what the people that were here before us changed. So there also could be some things that were changed. I did recap this, but I recapped it with the same capacitors that came out of the board. So whatever value was in there, that's what I replaced it with. But that doesn't necessarily mean it's correct. So now we have to go through and figure that out. Well, that was a bit more of a task than I imagined it would be. So here's what I did. I just blew up this little section of that amplifier, and with a lot of whiteout and a lot of copies and a lot of measuring on the board, this is a accurate schematic. So the first thing you'll notice is where there used to be a capacitor coupling the two stages, we now have direct coupling. So if we look here, and well, you would have direct coupling if I in fact connected it. So what we have now is we have something that looks kind of like this. And something like this. So these two stages are direct coupled. And you can see the voltage divider here. You have a 22K and a 22K on both sides. So this took quite a bit of doing to figure out. But essentially, this is what we have here. Actually, it's a 22K and a 2.2K. So that's written incorrectly. This was a lot of work to figure out. Or I'm sorry, it is 22K and 22K. My fault. So this is the accurate thing. Once I got this all figured out, and you can see even the emitter and collector were swapped around here, because remember, this was an NPN where the original schematic had it shown as a PNP. So, and this 150K did not connect to the collector. It actually went around and connected to the emitter of the second transistor. So it's kind of like a feedback circuit. So there it is. The other thing was the polarity of this capacitor was backwards, the plus and the minus, although I don't know how much difference that would make, being that these are both kind of at the same point. I don't know. But I put it in this way. Long story short, I put everything together this way, made sure it was proper this way, and when I turned it on, this was the result. There's your right and left channel at the record output jacks of the stereo. And if I move over here, right channel, and look at that, left channel. So beautiful. So there you have it. That's about as good as you can get it, I think. There is a little bit of adjustment yet that I have to do. I'm getting the tiniest bit of clipping, and it's equal on both sides. And again, I think that has to do with that potentiometer at the front end there. So try to move that out a little bit and see if we can straighten it. But that's pretty darn good if you ask me. So anyway, there you have it. It's working, and I think we're ready finally to connect an antenna and actually listen to it. Alright, we're going to take one final look here before we put it all together and put the covers on and give it a final test and hook up an antenna and listen to it. And you can see I upgraded the output capacitors. I moved them up to a 2200 microfarad instead of a 1000 microfarad. It should help a little bit with the low end distortion. It's not going to make a huge difference, but it will help a little bit. This is definitely an undersized power supply for this amplifier, but it is what it is. This will be, I mean, it's rated at 32 watts per channel, but really I would call this a 20 watt per channel receiver. It'll be very good at 20 watts per channel. All right, let's cover it up and test it out. All right, there it is. But I will tell you that it still has that little tiny bit of buzzing noise in the only when the tuner is turned on. It's dead silent as far as the amplifier. And somebody in the comments actually had one of these that did the exact same thing. I guess that's kind of a trait with this. If the volume is all the way down and you're not listening to a radio station, you hear just a tiny little bit of hum in the background. Of course, I have the air conditioning going down here, the fan's blowing, so it's kind of not very good. But let's turn it up. I can't do much because on FM everything's music and it's all copyrighted, so
faster and faster. Yeah, people shouting.
They're coming to record music.
Complain about, and sometimes I really have to catch myself and.
Not very good reception tonight. Probably nothing down here. I didn't think there would be. But anyway, not very good reception down here. And this is not the most sensitive receiver on earth. I mean, it's not bad, but certainly could be a lot better. But it works, and you can see it was toggling back and forth. And without getting some better reception, it'd be hard to really demonstrate this, but it works. Not too bad considering what all we went through to get it to function, and you saw in the scope at least that it is capable of reproducing a clean signal. So let's turn it on to auxiliary, and I really like these little, I didn't have to do anything with these. The lights were all good on this. I guess that was the only thing that was good at all. So let's listen to some YouTube safe music. Of course, I don't know how my lapel microphone's going to pick this all up, but loudness switch. So, hey, it's working. It sounds good. It's performing well. And, wow, this was a job. I don't know that I will ever do one that was this far gone ever again. I don't know. Of course, I said that a couple of other times where I had some basket cases, but this one was in particularly bad shape, and it didn't, on the outside, didn't look so bad. So, I don't know. But who knows what kind of history. Boy, if this thing could talk, could imagine the story it could tell. Well, let's get the cover on and see what it looks like all finished. Yep, there it is. Ready to boogie back into the 70s. And it's all fixed. All rebuilt. And good for the next 30 minutes. Or should I say years? Seconds? I don't know. No, all kidding aside, I think it's working pretty well. I've been playing it for a while and everything works. And Well, so ends another project. So again, I couldn't have done it without all of you. Thank you guys so much, all of you, for all of your comments and all of your suggestions. I'll tell you, you all came out of the woodwork with schematics and advice and so forth on this, so I really like that. That's the part of this channel and that I enjoy the most, so thank you all. Again, as always, I wish you all peace, joy, happiness, and good health. Until the next time we meet again here on the next project, I wish you all well. Take care. Bye-bye.